Okay, everyone, so it's 7 o'clock, so we're gonna get started. So just give me 1 second to pull up the PowerPoint. So tonight we're gonna be covering chapter 13. The challenge problems that we're gonna go over do have to do with chapter 12, but we're doing all new material tonight so we don't get behind. If you are looking for chapter 12 stuff, we finished it last week, so maybe check out a previous SI. But yeah, so tonight we're going through new material, and then on Wednesday, we'll be doing a review of chapter 11 and 12. And the challenge problems on Wednesday will have to do with chapter 11 and 12, because that's trying to get you prepared for your exam on Friday. Okay, so one comment about the challenge problems is there was one number that I had to edit in number 7, and I knew I had to edit it and I forgot to change it. And so when you solve for the activation energy, it actually would have come out negative and wrong. And so I'm not going to go over that tonight. Instead, I'm recycling it as one of tonight's challenge problems. I've made the adjustment to the problem, so it can now be done. And we'll go over that on Wednesday, because that problem will be a really good review on chapter 12 anyways. So we'll, again, go over that Wednesday. Okay, so number 1 was just a theoretical question about rates. And so, we have 3 options, basically A, B, C, and then the rest of the options are just different combinations of those. Okay, and so A says, given the same rate constant, so given the same K, a second order reaction will always have a higher reaction rate than a first order reaction. Okay, and so one strategy I have for questions like this is always try to disprove a statement, right? So this one says always, and it's very hard to find always statements that are true. And what you'd find if you start taking example first and second order reactions is this is true when our molarity is greater than 1, right? So if you write a first and second order reaction with, let's say, 1 reactant, and you plug in for your concentration some number greater than 1, A would be correct. But it's not always correct, because if our molarity is a decimal, so less than 1, this statement A won't be true, or won't necessarily be true. Okay, so that's why A would not be correct. B, temperature does not affect zero order reactions as rate is independent of the reactant. Kind of the second portion of this statement is just, it is true. Zero order reactions the rate is independent of the concentration of reactant, but the temperature still has an effect on all of our rates. Okay, so B would be true. B would be false because it does have an effect. We can see this in our Arrhenius equation along with that that CC equation. That's what I call it because I can't pronounce it. Okay, but we have multiple equations that show us that despite whether it's a 0, first, second, whatever order reaction, our temperature does play a role on our rate. C, temperature generally increases the rate of the reaction by lowering the energy barrier, or the activation energy. Although it's true that when we increase temperature, the rate of the reaction typically increases, it's not, it doesn't do so by decreasing that energy barrier, right? It just gives your particles more energy to try to overcome it, right? The only way we decrease energy barrier is through catalysts. Okay, and so the answer here should have been none of the above, F, and again, these reasons kind of just describe why. Okay, 2, which of the following best describes what frequency factor, or A, is, right? So we see this in the Arrhenius equation, right? And I'm actually just going to go, so kind of take note of the options here, but I'm going to compare our Arrhenius equation to collision theory equation, right? These are both 2 different equations that represent what K, our rate constant, is, right? So collision theory says K equals P times Z times F, which P represents is the orientation correct? Z represents how many collisions there are, and F represents how many collisions have enough energy to actually become products, right? And when we compare this to the Arrhenius equation, this E raised to our negative activation energy over R kind of corresponds with our energy portion of collision theory, right? So this F is kind of represented by E raised to the negative EA over RT. While our P and Z portions, which have to do with orientation and frequency of collisions, these are represented in our Arrhenius equation by this frequency factor A. Okay, and so in essence, our frequency factor is those two variables, and that correspond with option C, right? If you read each of those multiple choice options, these are kind of the variables in collision theory that each option corresponded with, right? So A kind of just described our Z portion, option B kind of represented Z and F in collision theory, while C, the correct answer, represented Z and P. Again, orientation and frequency. Which of the following statements is false regarding a catalyst? So A, catalysts are not used up in a reaction. That's actually one of probably the most important hypothetical point you should kind of understand about catalysts. It kind of always comes up one way or another on exams. And so that's true. They're not used up. B is false. We'll come back to it though. I want to show a little diagram I drew on the next slide. C, a catalyst decreases the activation energy of a reaction. That's absolutely true. That's how it works. That's how it makes the rate go quicker, by decreasing that energy barrier. D, a catalyst can be classified as heterogeneous or homogeneous. That actually is true. I know you guys don't talk about that too much in lecture, but that's a small little point that has appeared in the past, so I just wanted to kind of bring it up. That can be true. It just kind of depends on what state your catalyst is in. And so A, C, and D are correct, and B is false. They do not reduce the measure of a state function, right? And I want to show that on the next slide, right? So this is an energy diagram showing our reaction with no catalyst in solid line, and then the dotted line, this is our reaction with a catalyst. Now remember what state functions were. We learned this last semester when going over thermochemistry, right? State functions are, or state properties, state variables, they don't depend on the path taken during a reaction. They just depend on our original state and our final state, right? And so in terms of a reaction occurring, right, our initial state and our final states are energies, right? Our initial energy of our reactants and then the final energy of our products, right? And as we can see, whether we have no catalyst or a catalyst here, what we start with, that energy level, and what we end with, that energy level, doesn't change at all, right? So the state variable, the state property, isn't going to be affected by the catalyst, because all the catalyst does is decrease this activation energy, which changes the path of the reaction. But again, state variables or state functions, whatever you want to call them, they don't depend on the path of the reaction. Okay, so catalysts, that's why B is false. Catalysts don't affect state variables. Okay, which would be like change in enthalpy, change in Gibbs free energy, which we'll talk about in a couple chapters. But of state functions, you're probably most familiar with change in enthalpy, which was our delta H from last semester. Okay, number 4 is a very classic multiple choice problem from this chapter. And so you graph the natural log of K versus 1 over time, right? So your y-axis would be the natural log of K, 1 over time would be your x-axis, and you get a straight line with a slope of negative 8.42 times 10 to the second K. What is the activation energy, right? So it's important to remember that this graph is kind of based on our Arrhenius equation when we take the natural log of the entire thing. And when you take the natural log of our Arrhenius equation, right, the portion that is attributed to the slope, right? So our slope would be equal to negative activation energy over R. Okay, so all we have to really do in this problem is say that our slope is equal to that, right? We're solving for our activation energy, and we know our R is 8.31 joules per mole Kelvin. When you solve for activation energy, it comes out to about 7,000 joules, which wasn't one of the options, and so we convert it to 7 kilojoules, which was option D. Okay, so just kind of keep this. This is one way that they love to present information, right? This natural log of K versus 1 over time. And typically they'll ask you about the slope, right? Because the slope we know is related to our activation energy. The other thing that you should note is that your y-intercept corresponds with the natural log of A, right? A is that, sorry, I'm messing with the frequency. I kind of forget what it's called. Go back. Sorry, frequency factor is A. Sorry, I completely spaced on the name there. Okay, so natural log of A, that frequency factor, would be your y-intercept when you plot the natural log of K versus the inverse of temperature. Okay, number 5 is just kind of a straightforward find the half-life problem. Right, typically in every problem we've done so far, I'll give you the half-life, and typically you solve for K and then use that K to do something relating to the integrated rate law. But here it was just simply plug into our half-life equation for first order reaction and find half-life. So our half-life for first order reaction is equal to 0.693, which this numerator is just the natural log of 2. Okay, and we divide that by K. We were given K in the problem. It's 0.035 seconds to the negative first. And when we do this division, our half-life comes out to 19.8 seconds, which was option A. Okay, and then again, the last one we're going to go over tonight, just because number 7 will be recycled for tonight, and it's just at the end because I had to make an edit to it. Here's an example problem where we get 2 K values, so 2 different rate constants, and we're actually, in this case, solving for an unknown temperature, right? So we're going to have to use that CC equation, which allows us to use all that information, right? So I'm going to start out just by writing all the known information because there was quite a bit. And so K1, I'm just going to denote or kind of represent it with the 12 degrees Celsius information. So K1 is my rate constant that's associated with that temperature. So 0.049 seconds to the negative first. My temperature for that, again, is 12 degrees Celsius, but we don't care about it in Celsius. We have to convert it to Kelvin to eventually plug it into our equation. So 12 degrees Celsius is 285 Kelvin. My other rate constant that I know is 0.284, but we are unsure of the temperature associated with that, right? That's what we're going to actually be solving for in this problem. Okay, and then we were told that graphically we were able to find the slope and the activation energy, which came out to 51.6 kilojoules. I just converted it to joules so I could plug it into the equation below. Right, and so this is the CC equation. That's just what I call it for short. So the natural log of K2 over K1 is equal to the negative activation energy over R times 1 over T2 minus 1 over T1. Okay, you might be familiar with slightly different versions of this equation. I recommend you use it in this form or whatever form appears on your equation sheet, right? The presence of a negative sign here can kind of change how you order some things in this equation. And so just stay consistent. That's all I'll say. That's something that came up last SI. Okay, so this is the form I use, and I'll always use this form. And so what I do is I just plug in all my information, right? So the natural log of K2, which I'm going to use as this 0.284 number, divided by K1, 0.049, is equal to my activation energy, and it's in terms of joules, right? So 51,600. And the reason I converted this to joules is that my R constant here, 8.31, is in terms of joules. okay? I could have converted this R to kilojoules per mole Kelvin, but instead I just decided to change my activation energy. It seemed a little bit easier to me, okay? But as long as they're both the same units of energy, so joules or kilojoules, it's fine. You'll get the same answer. Okay, so I personally chose joules. I plugged in those values, and then it's equal to 1 over T2, which we're not sure. That's what we're solving for, so I'm going to denote it with X, minus 1 over T1 in Kelvin, which is 285. And I went through these calculations, and I eventually found that X was equal to 310 Kelvin, which corresponds with 37 degrees Celsius. Okay, those are all the challenge problems that we're reviewing tonight. Are there any questions on any of those? And if they're not, if you don't mind just signing in using your net ID, that would be awesome. And then I know that you don't have questions. So I'm kind of going to wait for people to respond.
I have a quick question about the CC equation.
Yes.
So, you might have already said this, but where does the negative activation energy come from? Because I know, like, on our equation sheet, it's the exact same equation, but it's positive.
Are any of your K's or temperatures flipped? Is it like T1, T2, or K1 over K2?
Oh, okay.
I
So,
think says, I think your equation on your equation sheet is 1 over T1 minus 1 over T2, and it's positive activation energy over R, correct? Mm-hmm. Yeah, and so I do it in this order and have the negative sign, just because I'm pretty sure when I was taught it, it did have a negative sign, and over the 4 or 5 years, this has just kind of become ingrained in me. Again, whichever equation you use, that's fine. I would just recommend stay consistent. Because either of these will work. When you plug in your values, it should come out exactly the same either way. And so, yeah.
Okay, and then also on this same slide, when you have 1.757 equals negative 6,000, that step, how did you like get isolate the 1 over x minus 1 over 285?
So from where my pointer is right now, my mouse?
Yeah. Mm-hmm.
So you divide both sides by negative 6,209.
Okay.
Which gives us this really, really small number. I kind of didn't even see the times 10 to the negative fourth at first. That's why it almost looks like an afterthought, because it was, right? So it's a really small number. Then you add 1 over 285 to both sides. You get a really, really small positive number here. It's equal to 1 over x. And then you just do 1 divided by this really small number to find what just x is.
Okay, thank you.
A really good way to self-check yourself here, if you, I'm trying to remember what I did. I accidentally plugged it wrong into my calculator, and when I ended up solving for my temperature at first, it came out to about 265 Kelvin. Okay, which that's a number and it's feasible, but I asked myself, I'm like, does that make sense? And I went back to the very top, right? K1 is about 0.05 and the temperature is 285 Kelvin. Now, what I know about reactions and how fast they run and temperature is that as temperature increases, my rate constant should increase. Therefore, my rate should also increase, right? So because K2 is greater than K1, right? It's a lot bigger. I knew that my T2 should be bigger than my T1, right? So when I miscalculated and got that my temperature was 265 Kelvin, I kind of knew that that shouldn't be right because that's a colder temperature and that the real answer had to be warmer than T1 because my K2 is bigger than K1. Just a way you can kind of use these equations. Sorry, there's another question in the chat. Should we expect all math problems to be like plug and chug with our equations for this chapter? That's hard to really comment on. I mean, anytime you're using equations, it's going to seem somewhat plug and chug, but they will definitely present information in a way that challenges your understanding and your conceptual understanding, your hypothetical understanding of this material. And so I think where a lot of students struggle in this course is their tendency to feel like these chapters are just plug and chug, plug and chug, plug and chug. And then they kind of get blindsided by how much conceptual understanding is really required, especially in Chem 1128. The conceptual questions, they definitely increase the frequency of them. And so, yes, there is a lot of plug and chug portions of it, but yeah, I don't want to dismiss the conceptual side. And so, again, tonight's challenge problem number 6, which was it was number 7 from last Wednesday. I think that's a great plug and chug question, but it also requires a very high level of conceptual understanding. Okay, so if anybody, I suggest everybody before Wednesday try. I believe it's the last challenge problem tonight. I think it's number 6. Definitely try that because, again, it does require a lot of conceptual understanding along with the mathematical backing. Okay, so jumping into chapter 13, we're just going to cover a lot of what you cover in lecture this week. There's maybe 1 or 2 examples that we'll kind of save for next week when we dive into chapter 13 a little bit more. But in terms of material from chapter 13, this really covers most of what you'll go through in lecture. So we're going to start talking about equilibrium, what it is and what the equilibrium constant is. Then we're going to go through an extremely traditional type of question, which I just call table problems because, well, they involve a table and will always involve a table. Just the way they present that information hasn't really changed in 5 years. Then we're going to go over what the reaction quotient is. And then lastly, we're just going to talk about manipulations of K, which K is our equilibrium constant. Okay, and so up to this point in Gen Chem 1 and also Chapter 11 and Chapter 12 this semester, we've kind of only focused on what we'd call the forward reaction, right? Our reactants are on the left, our products are on the right, and we kind of only see it moving in one direction. But if we actually look at chemical reactions, almost every single reaction goes in what we'd consider the reverse direction, or the reverse reaction will occur, and it will occur to a certain extent, right? Typically, it won't be as great as the forward direction, which again, when I say forward and reverse, forward direction will mean our reactants are on the left, our products on the right, and a reverse reaction is just the opposite of that, where our reactants are written on the right and our products are on the left, right, when we're looking at the normal reaction. Okay, and one of the major reasons why we see like the forward reaction predominant or favored is because of activation energy. Okay, so here are 2 examples where I've drawn energy diagrams, right? So that's what the y-axis is. And again, this is before, this is our reactants and our products are kind of at the bottom of the slope. And I'm drawing the activation energy, right? So looking at example 1, when we convert from A to B, right, our activation energy, which is just the energy that we must overcome to convert to products, is just the energy difference between our transition state, which is the top of the hump, and the energy of our reactant, A. So as you can see in this first example, our activation energy isn't that high, okay? And so we would predict that a lot of A, our reactant, is going to convert into product. Okay, but let's look at the reverse reaction. Okay, so this is the same exact reactant product, but this time we're doing the reverse reaction, right? Where we're going from B to A. Okay, and again, realize that the energies are exactly the same as before. It's again just written in terms of B to A. But look how big our energy barrier or activation energy is here. Okay, because there's such a big energy barrier, right? Not a lot of B is going to be converted backwards into A, okay? And so in example 1, we are going to see that the forward reaction is highly predominant, or it's highly favored while the reverse reaction, because of the giant energy barrier, will barely occur at all, okay? There's other examples, though, where this difference isn't as extreme. So let's look at example 2. So same exact thing, we have a conversion from A to B. Okay, and when we convert from A to B, we can see the energy barrier. It's pretty significant, but I'm sure lots of molecules of A will be able to overcome that to become B. Now let's look at the energy barrier for the reverse reaction, B to A. Well, the energy barrier for B to A is very similar to the energy barrier for the reaction of A to B. And so what example 2 shows is that although one direction might be slightly favored, if the energy barrier is somewhat similar for the forward and reverse reactions, you'll see more of each, right? So we'll see a lot more of A to B and B to A in example 2, while in example 1, we'll pretty much only see reactant A converted to product B. Okay, and again, that has to do with our activation energy barriers. Okay, now in rates, we have our rate constants, K, right? And so we have something now called an equilibrium constant, which we're going to denote with a big K. And all this is, it's a ratio of our rate constants of the forward reaction, right? So the rate constant for the forward reaction is going to be K, and our reverse rate constant, K with this little tick. We'll call it K tick, right? So this would be, K is just the rate constant for the forward direction, K tick, the rate constant for the reverse reaction. And our equilibrium constant is just a ratio of those. Okay, so how do we calculate this? Okay, so our equilibrium constant, K, is a ratio of our forward rate constant, K, divided by a reverse rate constant, K tick, which is equal in general to products over reactants, right? So if you're kind of just generally trying to look at our equilibrium constant, in general, it's products over reactants. And if you actually want to calculate it, it's going to be our concentration of our products raised to their respective coefficient, right? So C raised to the coefficient of C times the concentration of D raised to its coefficient, divided by our concentration of our reactants raised to their respective coefficients, right? So the concentration of A raised to whatever its coefficient is, concentration of B raised to its coefficient. Okay, so we're actually going to use our balanced chemical equations in this to solve for our equilibrium constant K. Okay, and what's really important is that we can solve for this or include things that are in our aqueous state, right? So aqueous state are just things that are dissolved. So they're going to have a molarity, right? So molarity would be the units, concentration, or we can include things that are in the gas phase, right? So in this case, we plug in the pressure in terms of atmospheres. Now it's really, really important, and students will forget this on the exam, it is important to exclude any reactants or products that are solids or liquids. Okay, so if a certain reactant is a solid or liquid, you just completely ignore it when writing the equilibrium constant and solving for it. Okay, just a couple other theoretical notes. Our equilibrium constant K doesn't have any units, right? So if they ask you to solve for K, you just write a number. There's nothing else to write. And we actually have different forms of K, right? Because we can solve it when our reactants and products are in the aqueous dissolved state, right? So in terms of concentration, or we can solve for K when our reactants and products are gases, when they exert a pressure. Okay, and this equation here, I believe is not on your equation sheet. So I would definitely write it down and have it in your notes for when you take the exams. But this allows us to convert between our equilibrium constant in terms of pressure and in terms of concentration. Okay, and so this says that our equilibrium constant in terms of pressure is equal to our equilibrium constant in terms of concentration multiplied by R, which R is going to be our ideal gas law constant, the 0.08206 number, times our temperature, which is going to be reported in Kelvin. And this RT portion is going to be raised to the delta N power. And delta N stands for change in number of moles of gas. Okay, it's really important that it's only of gas molecules. Okay, and so what you do here is you count how many moles of gas you have on the product side, and from it you'd subtract moles of gas on the reactant side. Okay, so basically to do this, you would just look at your reactants and products, and ask what is in the gas phase, and then to know how many moles of that you have, you just add up the coefficients on each side, right? So if you have no reactants that are in the gas phase and you have one product that's in the gas phase and it has a coefficient of 2, then it would be 2 moles of gas on the product side minus 0 moles of gas on the reactant side. Delta N is 2. Okay. Are there any questions about those theoretical notes on equilibrium and equilibrium constant before moving on to kind of applying it and doing what I call chart problems? Okay, if they're not, we can look at the basic layout of a chart problem. So this is a really small data set. Typically, it'll be a lot more. Dr. Katie does go over this in lecture in, I believe, the first lecture video, if you want another example. But we're going to use this example equation above, right? So 3A, whatever that is, in the aqueous state plus 2B goes to C, right? And we're given some data points. Just note that this dash means 0. There's no initial concentration of C. And as time goes on, we see our concentrations fluctuate, and eventually we get to equilibrium. Okay, so I just want to talk about general table problems before moving on how to solve this. So in Dr. Katie's example that he did in lecture, you know you're at equilibrium because he gave you multiple data points or multiple time points where our concentrations don't change. Okay, so that's one way to indicate. And so that's one way to indicate that you're at equilibrium. Another way to indicate that you're at equilibrium is how I did it here, by just telling you this is going to be equilibrium. The third way is that they could not tell you at all where equilibrium is. You just have multiple different time intervals. And typically, if they give you no indication as to where equilibrium is, you just assume that the final experiment or the final time point is equilibrium. Okay? Somebody asks, are these similar to ice charts that we're going to do later? Somewhat, I would say not really. Ice tables are a little bit different. Don't worry about ice tables yet. Okay, and so let's look at how to actually solve for these unknown values so that we can know what our equilibrium concentrations are, and then we're going to solve for our equilibrium constant. That's the goal of this problem. But before we learn how to fill in unknown portions of information in this chart, let's look at the data points that they actually gave us to figure out how we can make these jumps. Okay, and so this is our information for minute 0, and over here is our information for 1 minute in. Okay, and in the middle, I wrote a column that says this is delta, right, meaning change. Okay, and let's just go back for a second and look at our balanced chemical equation. Now we know from chapter 3 or 4, whenever it was, way back when, that if this is our balanced chemical equation, it means that we would need 3 molecules of A to react with 2 molecules of B to create 1 molecule of C. Okay, and so basically, we're going to use 3 times as much A as compound C that we produce, and we're going to use twice as much B as compound C that we produce, right? It's a 3 to 2 to 1 ratio. Well, that's the same principle that we're going to apply to these problems, right? And so we're going to represent the change in A by calling it negative 3x. Okay, x is just kind of a common number to kind of compare these three different compounds. The negative indicates that it's a reactant, right? A is going to be disappearing because it's a reactant as time goes on. And the 3 is just the coefficient of A, which basically just allows us to talk about how fast it disappears in relation to other chemical compounds. Okay, so the change in A is going to be represented by negative 3x. The change in B, because it's a reactant and it has a coefficient of 2, is going to be negative 2x. And the change for C is going to be positive x, because the coefficient of C in the balanced chemical equation is 1, and it's going to be positive because C is a reactant, so it's going to be appearing. Okay, now if we look at data from minute 1, right, we can actually solve for the value of x, right? X equals 0.04, right? And we know that because at minute 0 to minute 1, C increases from 0 concentration to 0.04. So 0.04 is equal to x, right? We see for B, 2.7 minus 2 times x, which is 0.04, gave us the 2.62 number that was in the table. Same thing for A. We take 3.45, we subtract from it 3x, so 3 times 0.04, and that gave us the concentration at minute 1. Okay, so we're going to apply the same exact logic just for information we don't know. Okay, so here's our data from minute 1, and here's our data from minute 2. Now, the only value we were given in the table is the number I circled, 0.3. Okay, and so from minute 1 to minute 3, our concentration of C increased from 0.04 to 0.3. This means that our change, which for C should be represented by just x, is 0.26, right? X equals that difference, 0.26. So if x equals 0.26 here, we can apply that change to our other two chemical species, right? So B, the change from minute 1 to minute 2 should be negative 2x, right? And if x is 0.26, it's going to be negative 2 times 0.26. We do that change and find that the concentration at minute 2 should be 2.1. Okay, we do the same thing for compound A, negative 3 times x, which is 0.26. And when we do that subtraction, we find that the concentration of A after 2 minutes should be 2.55 molar. Okay, now that we have the data points for 2 minutes for all of our chemical compounds, we can look at the next data point, which would be at equilibrium. So again, the only data point we were given was for compound C, and we were told that at equilibrium, its concentration is 0.32. Okay, now the change, again, for compound C would have been equal to positive x. Well, positive x, that change, is equal to our concentration at equilibrium minus our concentration at 2 minutes. So x here is equal to 0.02. Again, we plug that in for B and A to find our equilibrium concentrations. Okay, and so at equilibrium, our concentration of A should have been 2.49, our concentration of B should have been 2.06, and our concentration of C should have been 0.32. Okay, from here, we want to solve for our equilibrium constant. So our equilibrium constant in terms of concentration, right, because we're dealing with molarities here, is equal to the concentration of my product C raised to its coefficient. So its coefficient is 1. So it's C raised to the first divided by my concentration of A at equilibrium raised to the 3rd power, because that's the coefficient of A, times the concentration of B raised to its coefficient, the 2nd power. Okay, and so all I do is I plug in my equilibrium concentrations, and I can solve to find that Kc is about 4.88 times 10 to the negative 3rd. Okay, so this is a very reoccurring type of problem that I really think has been on an exam for the last 4 years. So if it's on this year's, it'll be 5 years in a row. And so again, Dr. Katie also goes over an example. There's another one that's an example in the challenge problems tonight. So I highly recommend you all get very familiar with how to do these types of problems. Okay, are there any questions on that before we talk about reaction quotient? Okay, if there are no questions, so reaction quotient, I think sometimes confuses students because they struggle to see how it differs from K, our equilibrium constant. Okay, so reaction quotient, we use Q to represent this. And really what it does is it kind of tracks our direction and progress towards equilibrium, right? So it's kind of saying, where are we in relation to equilibrium? Which direction are we going? And how far are we from being in equilibrium? Okay, and how do we actually calculate this reaction quotient? Well, when we look at the equation, from a very superficial view, our reaction quotient Q is equal to products divided by reactants. And for our general basic equation that we use, A plus B goes to C plus D, this is how we solve for Q, our reaction quotient. Okay, and so what you'll notice is it's exactly like solving for K. There is genuinely no difference in the way you solve for Q compared to how you solve for K, or equilibrium constant. The only reason we use Q is we use it when it's kind of more of a proper, like a proper way to write it. Really, we just write it or use it when we're not at equilibrium or we're not sure if we're at equilibrium, right? So if your professor just gives you a bunch of data points and values, and you're trying to find your equilibrium constant, you should really write Q equals all those values, because unless you're told you're at equilibrium, it's just correct to write Q. Okay, and so in your typical problem, what they'll do is they'll give you a bunch of concentrations or a bunch of pressures, and they'll tell you your equilibrium constant is some value. Are you at equilibrium? Right? And so that's actually what we're going to do on the next slide. So I'll kind of just let us get there. But and based on our relationship between Q and K, we can know the direction of the reaction, right? So this chart down here is very, very important, right? So if we solve for our reaction quotient Q, and the value of Q is less than the value of K, our equilibrium constant, it means our reaction is going to keep going in the forward direction, which is our left to right, right, when looking at an equation. Basically what it means, and again, remember Q generally means products over reactants. If Q is less than K, right, that means it's too small of a number, meaning it needs to increase, and Q can increase by converting reactants into products, right? Q will increase by increasing the number of products we have, which is in the numerator. Okay, and so that can help you realize that, oh, if Q is less than K, I need more in the numerator, which means I need more products, which means I'm going to be going in what is traditionally the forward direction, so that Q can eventually equal K. Okay, if Q is equal to K, that means you're at equilibrium, right? So no particular direction is favored. In the slides, it says no reaction. From my understanding, I believe there's still some back and forth at equilibrium, but you are at an equilibrium. Okay, so there's no real net direction. Neither direction is favored. Just some reactants will become products, some products will turn back to reactants. And then lastly, if Q is greater than K, right, that basically means you have too many products and not enough reactants. That's why your Q is too high. And so your reverse reaction or reverse direction will be favored, meaning you're right to left. Okay, and so let's actually look through an example and see how we'd apply this. Okay, so up above is a balanced chemical equation. Right, and it says you want to test if the above system's in equilibrium, you have a certain amount of water, and you're given a bunch of partial pressures of all the chemicals in the system. If the equilibrium constant, K, is 0.88, is the system in equilibrium? If not, which direction should it move in order to reach equilibrium? Okay, so that's the first part of the question. The second part says, if all pressures besides nitrogen monoxide are kept constant, what pressure of nitrogen monoxide would cause the system to be in equilibrium? Okay, so this second part actually kind of indicates that in the first part, you're not going to be at equilibrium. But let's prove that, and if we're not at equilibrium, try to figure out which direction we should move in. Okay, so our reaction quotient, or Q, is equal to the pressure of SO, SO, sulfur monoxide, times the pressure of diatomic nitrogen, divided by the pressure of nitrogen monoxide. And notice that we squared this because the coefficient of nitrogen monoxide in our balanced equation was 2. And we're going to multiply that by the pressure of dihydrogen sulfide. Okay, and all I do here is plug in the values given to me in the problem, right? And I solve for Q, and it comes out to 1.41. Okay, so now that I found my reaction quotient Q, I can compare it to the equilibrium constant they gave me in the problem, right? They told me my equilibrium constant was 0.88. And so by comparing these values, I can find that Q is greater than K, right? And whenever Q is greater than K, 1, we're not at equilibrium, but 2, we have too many products, not enough reactants, and so our reverse reaction will be favored, which will be right to left when looking at the equation, right? So we're going to be converting SO plus nitrogen and water to dihydrogen sulfide and nitrogen monoxide, okay? The one thing I want to point out in case you didn't notice it, yes, water is in this chemical equation, but because it's a liquid, I left it out when calculating my reaction quotient, just like I would if I was calculating my equilibrium constant. Okay, so the first part of the question is no, we're not at equilibrium. The reverse reaction is favored, and we know this because when we solve for Q, it is greater than K. Okay, now the second part of the question said, if all the pressures were kept the same, except for nitrogen monoxide, what would the partial pressure of nitrogen monoxide need to be in order to be at equilibrium? Which again, our equilibrium constant is 0.88. And so I set that equal to my products divided by my reactants. Okay, here I don't know what my value of nitrogen monoxide is. Be careful, make sure you're definitely squaring it still because the coefficient for that is still 2. When you eventually solve for X, it comes out to about 1.71 molar. Not molar, sorry, atmospheres, because we're talking about pressures. Okay, but this is a very typical reaction quotient question. Plug in values to find Q, relate Q to a K that was given, and then based on that relationship, comment on which direction is favored, whether it's the forward reaction or reversed reaction, or are you at equilibrium? Okay, and then the last thing I want to talk about, we don't really have an example for this tonight. There are a couple challenge problems that address it, but it's manipulations of K, right? And so I would say, think back to thermochem when we did Hess's law problems. Remember when we added those delta H equations together, right? And sometimes we had to flip equations, we had to multiply equations by some coefficient, and then we had to eventually add equations together. Now, this is kind of looking at those same manipulations to the equations, but what we do to K in response to them. Okay, so for the examples that I use down here, I'm going to say that my original rate equilibrium constant is 4.38, and this is for the reaction of A going to B. Okay, and so if you're ever in a circumstance where you want to reverse your reaction, right? So you want to find the rate constant for the reaction of B going to A, right? You would find this by taking the inverse of your original K. Okay, so the rate constant for B to A would be 1 divided by our original, sorry, I said rate constant, equilibrium constant. It would be 1 divided by our original equilibrium constant, 4.38. When we do that division, it comes out to 0.228. Okay, so the equilibrium constant for beta A is 0.228. Now, WUMS, if you want to find the equilibrium constant of a reaction that you multiplied by some coefficient, right? So let's say we wanted to find the equilibrium constant for the reaction 2A goes to 2B. Well, all you do for this is raise your original equilibrium constant to the exponent. I think I wrote to the exponent. I was going to say to the coefficient, so I'm sorry. Right, so if we multiplied an equation by 2, we're going to raise our original k by that coefficient. Okay, so our new rate constant would be 4.38 squared, because that's what we multiplied our equation by. And so our new equilibrium constant would be 19.18 for that. Sorry for that little error. And then if you ever need to add equations together, it's not too common to have to do that, but if you ever add equation 1 and equation 2, you just multiply the k values together, right? So you multiply those equilibrium constants together. Okay, and that's all we have for new material. I didn't want to get too far ahead, but we will pick this chapter back up next week. But are there any questions on the material presented tonight before showing the challenge problems? Okay, so I will start to show them, and if people have questions, feel free to put it in the chat. So the one thing to note about these challenge problems, so they have to do with chapter 13, and so I believe we'll be going over these next Monday, right? I think we have enough to do on Wednesday between me going over chapters 11 and 12, and I want to leave plenty of time for questions, a little Q&A at the end, and so we won't go over these challenge problems until next Monday when we pick back up with chapter 13. But the last challenge problem, which has to do with chapter 12, we will review that at the beginning of Wednesday's session. Okay, so we're only going to go over one challenge problem at Wednesday's session, and it will be just the last of these challenge problems. One note on this, number 1, before moving on, is I ask here, what is the KP? And that is not mistaken, okay? I know that I'm asking for KP, and be careful because the data in this problem may or may not lead you to be able to solve for KC. And so you have to use an equation to then convert. But for 2 and 3, they kind of have to do with manipulations of K. Okay, and again, I think one just like number 2 is one that has been seen on exams as a multiple choice question. So these are potential ways you could see these delivered on an exam. Okay, move on to the next slide in just about 5 seconds if you need a picture of it. Okay, number 4 is a very classic reaction quotient question, right? So you're given a bunch of information, you're given a chemical formula, and then based on your calculations, we want you to kind of take a theoretical approach to the answer, right? What is the reaction quotient in relation to the equilibrium constant? And based on your calculations, what does that mean, those relationships? Okay, so that's number 4. Number 5 is using this chemical formula and the chart. Basically find Kc, so our equilibrium constant. Note here, again, I don't tell you where equilibrium is, so assume it's at this 6th data point. And so I would recommend, especially for practice, going through and trying to fill out this entire table. That's a great way to build up your confidence on these types of problems. Okay, and so again, these first 5 problems we'll be going over next Monday. And this problem, number 6, is what we'll go over on Wednesday. In the original problem, it said 1.46, but again, when you eventually go on to solve for activation energy, you get a negative value, and I didn't mean for that to be the case. It was supposed to be 0.46, not 1.46. Okay, so again, this is a great problem to definitely try before Wednesday. You'll definitely see this at some point on an exam, whether it's on a long answer or a multiple choice exam, I'm not sure. Okay, so that's all I have for tonight. So I'm just going to end the recording, but if anybody has any questions, as always, I'm happy to stay around and answer them.